Today I'm taking you on an epic journey through my all-time favorite story. Picture this, a clear sunny day, high up in the mountains, right before sunset. If you've ever spent a night in a mountain cottage, you know the magic that unfolds after dusk. I invite you to breathe in the overwhelming majesty of the stars and galaxies. My kids recently learned in school that the Big Dipper points to Polaris, the North Star that guided explorers for generations. If there was a planet around Polaris with astronomers observing our Earth right now, they might see Dschingis Khan as he's uniting the Mongol Empire. Likewise, when we zoom in on Polaris, we can look back in time for many centuries. Because the light that reaches us now left the surface of the star over 800 years ago. But this is just the beginning of our time-traveling journey. Next, let's hover over to the Crab Nebula, a stellar nursery in our Milky Way. The star that you see being born right now actually began its life 6,500 years ago, around the time humans first settled in Africa and Asia. Besides our galaxy, there are billions of other galaxies out there in the night sky. Our closest neighbor, the Andromeda Galaxy, sits a little below the star constellation Cassiopeia. The light from there takes 2.5 million years to reach us, showing us a galaxy at a time before even human ancestors were walking around on Earth. Contrast this with one of the most distant galaxies recently discovered by the James Webb Telescope, visible only due to the lucky circumstance of gravitational lensing. This effect occurs when a nearby galaxy lies precisely in our line of sight. Like a magnifying glass, it curves the path of the light from the distant galaxy and turns it into an enlarged symmetric ring. The light of this ring has traveled over 12 billion years, showing a galaxy from a time when neither the Sun nor Earth had existed. For an amazing presentation on the black hole lensing of this animation, just follow the link in the upper right corner. Are these quasar galaxies the earliest objects that we can observe in our universe? Yes and no. If we stick to visible light, it gets trickier. The light gets stretched on its journey due to the expansion of the universe. The light from the galaxy that we see today was UV light at the time of emission. The visible light was shifted into infrared. From even more distant objects, we would only observe radio signals. But what if we exchange our eyes for sensitive radio antennas? Then we observe the entire night sky glowing faintly, as if it was heated up to a chilling temperature of minus 270 degrees. Yes, it's cold out there, but not entirely. This faint radar light, discovered by accident as radio noise in 1965, comes from every direction, having traveled over 13 billion years. This glow is the afterglow of the Big Bang, marking the birth of our universe. Isn't it wild that this temperature is almost uniform across the full sky? Only very precise measurements can reveal tiny deviations. In one particular direction, the temperature is 3 millidegrees hotter, in the opposite direction 3 millidegrees colder. This fluctuation is caused by our own motion relative to the Big Bang afterglow. What if we subtract the average temperature and this dipole fluctuation? Is the night sky then completely cold and dark? Not even close. We uncover an amazing temperature pattern varying just a few microdegrees. These fluctuations paint the image of our baby universe at an age of only 400,000 years. At first glance, you might think these tiny temperature fluctuations don't matter at all. But actually, they are a big deal for cosmology and how we understand our universe. What I show you today is how scientists analyze these measurements. Essentially, almost everything we know about the evolution of our universe can be inferred from these fluctuations. So there are two main contributions to this cosmic microwave background. First, it reveals the state of the universe about 400,000 years after the Big Bang, and it captures everything that influenced this light on its 13 billion years journey. In short, it maps almost the entire history of our universe. We observe this radiation on a spherical screen surrounding Earth. Therefore, we employ spherical harmonic functions to understand this radiation and to separate its various contributions. You see, the existence of this primordial light is like a birth certificate of our universe. It is the smoking gun for the Big Bang theory. It tells us that everything kick-started from a super hot state and has been expanding and cooling ever since. Everything we observe today, from galaxies to stars, they are all born during this cosmic evolution. By understanding this history, we can actually peek into the future and the fate of our universe. This tiny dipole in the cosmic radiation is like a radar trap. It helps us to precisely pinpoint the speed at which we are moving through the space compared to the original primordial soup, where all structures, galaxies and stars began to condense and continue to do so. And the even tinier fluctuations on all imaginable scales basically are the foundation of our modern cosmology. All important cosmological parameters come straight from analyzing these tiny fluctuations, or at least have to stand the test of compatibility with them. Before we dive deeper, let's grab our mathematical toolkit and get cozy with spherical harmonic functions. You might recall these from chemistry. They are crucial not just for the big picture of the universe, but also for understanding its tiniest building blocks like atoms and molecules. Back in school, I remember thinking that these images were weird and confusing, and I didn't particularly warm up to them. They only lost their esoteric nature once I realized that they are just one peculiar example of a function type that pops up all over math and science. Sometimes seeing the big picture helps making sense of things, so let's take a quick detour into the club of harmonic functions. You probably know the simplest members in this club, sine and cosine functions. They are harmonic because their second derivative is just the same function up to a negative factor. Think of a pendulum. The law of gravity says that its angular displacement roughly satisfies such an equation. That's why its motion can be described by a cosine function, at least for small swings. When the amplitude gets larger, the cosine is only a poor approximation of the actual motion. This is where harmonic functions really shine. Joseph Fourier figured out a while ago that you can approximate any function on a finite interval with combinations of higher harmonics of sine and cosine functions. Just like in music, harmonies are created when you include multiples of the base frequency. To sum up, we name the operator that converts a function into its second derivative the Laplace operator, usually symbolized by the Greek letter delta. Any function that only changes by a negative factor under the action of this operator is called harmonic function. There are two infinite families, the sine and cosine functions. According to Fourier's theorem, any function on a finite interval can be expressed as a sum of these harmonic functions. The notation simplifies further when you don't mind to combine sine and cosine functions into a complex-valued exponential function. The squares of the frequencies are the eigenvalues of the Laplace operator. When the start and end point of the function is the same, we can morph this interval into a one-dimensional sphere without changing anything. With a circle of radius 1, we can simply exchange the x-coordinate by an angular coordinate phi. Moving to 2 dimensions, there are no surprises. The Laplace operator gets an extra second derivative in y direction, and the harmonic functions become combinations of sine and cosine functions in x and y direction. Again, any function on this two-dimensional domain can be expressed as a linear combination of these harmonic functions. Spherical harmonics come into play when we look at harmonic functions on the surface of a sphere. So how do we turn a rectangle into the surface of a sphere? First, we crank our Laplace operator up to 3 dimensions. Then we embed a rectangle that holds the parametrization for the latitude theta and the longitude phi into 3-dimensional space. This is done using a specific parametrization of the sphere, which you may remember from my video on Riemann spheres. We also need to express the Laplace operator in terms of the spherical coordinates theta and phi. Doing this manually would be a drag, but if we throw some machinery at it, techniques from differential geometry or general relativity, it becomes a breeze. Now here's where the knowledgeable geeks come in. They tell you that the parametrization induces a geometry on the surface of the sphere, expressible as an infinitesimal version of the Pythagorean theorem for measuring distances. Notice how distances get shorter near the poles of the sphere. That's because the sign of theta drops to 0 when theta is equal to 0 or pi. This means that close to the poles any change in phi causes only a small change in actual distance. Then they would show you a universal formula that can compute the Laplace operator for any embedded surface that you can think of. Just like how distances depend on the latitude, also the derivative with respect to phi is scaled by the sign of theta. The spherical harmonics are the eigenfunctions of this particular Laplace operator, and they are denoted with YLM. The eigenvalues are computed from a positive integer variable L, known in science as the angular or orbital quantum number. The twist here is that there's not just one function for each eigenvalue. There are several marked by the second quantum number m, the magnetic quantum number, which takes integer values between -L and L. The phi part of the spherical harmonics is basically a sine or cosine function with frequency m collected in the complex exponential. The theta parts are given by associated Legendre polynomials, which can be computed using a master formula for any L and m. There is a normalization factor n, which ensures that these functions form an orthonormal basis. You might recall eigenvalues of matrices, which are omnipresent in linear algebra. You can think of the Laplace operator as an infinite-dimensional matrix, with the eigenfunctions in an infinite-dimensional vector space of functions on a sphere. Similar to their finite-dimensional counterparts, these eigenfunctions form an orthonormal basis, and any function on the sphere can be expressed as their linear combinations. Now you can see the expressions of the first few spherical harmonics on the screen, and we have thrown around enough mathematical jargon. Let's have a look at some animations. The spherical harmonics are defined as complex functions over the domain of the sphere, but don't let the word complex scare you. We can just look at the real or imaginary part, which is like extracting the sine or cosine function for the variable phi as we did before. The theta part is real valued in any case. The images you often see representing spherical harmonics are created by scaling each point of the sphere by the absolute value of the real part. The first function, the monopole, is constant everywhere, so the sphere just gets resized. Things get more interesting with the next functions. For the second one, the sphere gets squeezed to 0 at the poles, and at the equator the radius is periodically modulated by the contribution from the phi part. The third function is independent of phi and therefore symmetric around the z-axis. However, on the equator the radius of the sphere shrinks to 0, creating a similar dipole shape with two different signs indicated by the different colors. In general, the colors illustrate the complex phase. As the quantum number L increases, the details of these functions become more intricate. The remaining 5 functions are different components of the quadrupole moment. These names are inherited from multipole expansions commonly used in studying fields created by electric charge distributions. Now we are ready to return to the cosmic microwave background. It is remarkable how each of these base functions YLM contribute to the temperature distribution of the cosmic microwave background. We start with Y00, which is just a constant function. When we integrate its product with the measured temperature distribution over the full night sky, we get the average temperature, called the monopole of the spherical harmonics. Why does this temperature matter? This radiation, especially the anisotropies, provide a snapshot of the early universe. By understanding this temperature, we can figure out when this snapshot was taken and effectively determine a moment in the time of our early universe. Let's first see how this cosmic picture forms. Beyond stars and galaxies, the universe mainly consists of hydrogen clouds. Light can pass through these neutral clouds and travel vast distances. But if we rewind time, the universe contracts. All scales, including the wavelength of light, shrink. Every single photon is shifted towards blue and ultraviolet light. Its energy increases until it ionizes hydrogen atoms. When this happens, stars and galaxies have not been formed yet, and a rather homogeneous soup of hydrogen turns into a plasma containing freely streaming electrons and protons. These free electrons heavily interact with the photons, blocking the light from streaming freely. Starting from here forward in time, there comes a moment when this plasma recombines into neutral hydrogen and light is scattered for the last time before it travels undisturbed until it hits the Planck satellite detectors, much like how light from your screen reaches your eyes. The Planck satellite was started by the European Space Agency and recorded the cosmic microwave background very accurately. This moment of forming neutral hydrogen is called recombination and happened 13 billion years ago. The plasma back then was very uniform, but areas of higher density scattered photons at higher temperature, and lower density areas scattered cooler photons, similar to how infrared images show different temperatures across a phase, indicating different densities of blood vessels. Now, to find out when the cosmic picture was taken, we need to understand the universe's expansion. An older video of mine explains how to compute the age of the universe using Friedmann's equation. Here is a summary. The equation found by Alexander Friedmann balances the expansion rate of the universe with its matter-energy density. By knowing today's matter-energy distribution and expansion rate, we can compute them at any other time and therefore trace the evolution of our universe accurately. As we will see later, from the temperature fluctuations of the CMB, we can determine today's expansion rate and matter-energy distribution very precisely. From the latest data of the Planck collaboration, the current expansion rate, known as Hubble parameter h0, is given by 68 km per second per megaparsec. Dark energy omega lambda makes up almost 69% and is the largest contribution to the energy matter content of the universe today, while ordinary and dark matter only contribute 31%. Photons and neutrinos add a tiny fraction. From the redshift of equipartition, it follows that today their contribution is less than 1 part in 1,000. Using these values, we computed the age of the universe with the following integral. This gives us an age of 13.8 billion years. We can use a similar calculation to pinpoint when the last scattering happened, capturing the picture of the early universe. Some physicists can reliably compute the temperature at which the background radiation ionizes hydrogen, namely about 3000 Kelvin. The temperature decreases as the universe expands. A0 and T0 are the scale factor and the temperature today, while Arec and Trec are their values at the time of recombination. By rearranging terms, we see that in a 1100 times smaller universe, the background radiation ionizes hydrogen and turns the universe into a plasma. Using the same integral, we can find the time when the temperature dropped below 3000 Kelvin, allowing protons and electrons to combine to neutral hydrogen. By changing the upper bound of the integral to 1/1100, we find that this recombination happened roughly 370,000 years after the Big Bang. When the average temperature is subtracted from the temperature distribution, the next standout feature is the dipole. This temperature difference is explained by the Doppler effect. Similar to the sound change when a police car zooms past, the temperature slightly rises in the direction we are moving and drops behind us. But before we start handing out speeding tickets, let's dig into our toolbox and see what spherical harmonics can do. 3 spherical harmonics can mimic any dipole moment. When we form a linear combination of all three components, the coefficients C11 and C1-1 need to be complex conjugates, and C10 must be real to get a real-valued temperature distribution. Therefore, we can replace these coefficients with three real parameters x, y, and z. An animation shows how x is making the dipole grow along the x-axis. Similarly, y and z create dipoles along the other two axes. When we crunch the numbers with actual data, we get the coefficients that simulate the observed direction and magnitude of the CMB dipole. Physicists then tell us that the relative temperature fluctuation is roughly equal to the observer's speed relative to the speed of light. From this we find a speed of 370 km per second. Let's put the speed into perspective. An airplane usually covers a quarter of a kilometer in a second. If it moved 28 times faster, it would become a satellite, and passengers without seat belts would float around due to the balance of gravitational pull and centrifugal force. Earth on average travels 30 km each second to complete its orbit between January 1st and the last day of December. Our Sun orbits the center of our Milky Way at 230 km per second. Even combining all these motions cannot account for the speed relative to the cosmic microwave background. The only explanation is that our galaxy itself moves around the center of a cluster of nearby galaxies, so that all velocities eventually add up to 370 km per second. It might seem tricky to grasp the reference frame for this speed, since the background radiation itself travels with the speed of light. But this speed is measured relative to a distinguished cosmic frame of reference. It's the frame where the primordial cosmic soup was homogeneous, or if you wish, the frame where the Big Bang happened everywhere at the same time. The next animation showcases how multipole moments for larger values of L look like. For each given L, we smoothly vary the size of the contributions for different values of the magnetic quantum number m. You'll notice that as L increases, fluctuations with smaller features appear. In the second replay of this animation, we combine the contributions for the shown values of L into one single temperature distribution. Up to which value of L can the data be extracted from the Planck satellite measurements? Well, the Planck satellite measured the temperature fluctuations up to L equal to 2500. Whereas L equal to 1 corresponds to a scale that stretches across 180 degrees or half the sky, L equal to 2500 corresponds to a tiny scale that stretches only across 7% of a degree. You would need about 50 such tiny disks to cover the full moon. But don't worry, we don't need to discuss the multipole moment for each L separately. According to our current understanding, the primordial origins of these fluctuations are ultimately random processes from their initial quantum nature. This means models can't predict the temperature in one specific direction, but they can predict correlations between them, similar to standard deviations. For the analysis of the microwave background, the following correlations are used. The values are slightly rescaled and conveniently plotted inside a coordinate system. The first 50 of these values are hard to interpret. However, when we include data for larger L, suddenly a peak appears around L equal to 200, and more peaks follow at regular intervals. It seems like fluctuations of sizes that correspond to L equal to 250, 500, 750 and so on are more intense than others. Who would have guessed such regular patterns from the seemingly random fluctuations at the night sky? The locations and the amplitude of these peaks encode numerous cosmological parameters. Before we decode them, let's first understand how these peaks are formed. We've learned so far that the primordial light we see today was emitted by a plasma of protons and electrons. The fluctuations in this radiation are related to tiny density fluctuations in that plasma. Denser regions had a stronger gravitational field and attracted more protons, making them even denser. But why didn't these fluctuations grow larger before recombination? The photons play the key role here. Denser regions trapped more photons due to higher numbers of electrons. This radiation exerted pressure that balanced the gravitational pull, keeping the fluctuations small. Only after recombination, these denser regions eventually further collapsed to form galaxies and stars. The tiny fluctuations are described by linear equations, which predict waves that spread out through the plasma, much like sound waves travel through the air, however with a surprisingly large speed of sound that was roughly half of the speed of light. Fluctuations of different wavelengths interfered with each other. The linearized Einstein equations in such an expanding universe also show that there is a maximum wavelength that can travel through the plasma. This largest wavelength corresponds to the sound horizon, which is the distance such waves could have traveled since the universe began. Similar to a pipe that has a largest resonant wavelength or base frequency, waves with this largest wavelength resonated in the early universe. They got amplified together with their higher harmonics. They created the cosmic harmony that we can see in the power spectrum of the temperature fluctuations. We know the time when the light was scattered for the last time. This allows us to compute the size of the sound horizon very accurately, and the scale at which we observe this horizon today corresponds to the location of the first peak in the power spectrum. The current expansion rate or Hubble parameter significantly influences the power spectrum. It changes the evolution of the universe at all times. Like other parameters, it shifts the position of the peaks, but most distinctly, it changes the relative heights of the peaks. The best fit to the observed power spectrum is given by a current expansion rate of 67.5 km per second per megaparsec. Plotting the power spectrum on a logarithmic scale allows us to include more peaks and highlight the nearly constant power on the largest scales. There is a strong case for a spatially flat universe, meaning the angle sum of all triangles is always 180 degrees, no matter how large they are. However, we do not detect enough matter to satisfy Friedmann's equation for a spatially flat universe. This is the reason why scientists assume the existence of dark energy, which causes the universe to expand faster in the late times. This makes us observe the sound horizon at a smaller angular scale. If we replaced the dark energy by additional matter, the late-time expansion would slow down. We would observe a larger sound horizon, and the peaks in the power spectrum would shift to smaller values of L, which is best observed for the smaller peaks. Alternatively, we could replace the dark energy with spatial curvature. This would shift the spectrum into the opposite direction. The power spectrum is also sensitive to the ratio of visible to dark matter. Unlike visible matter, dark matter is not coupled to the photons before recombination, so it doesn't contribute to the sound waves and starts structure formation much earlier. Dark matter is also crucial for describing galaxy dynamics today. One of the greatest successes of cosmology actually is that the amount of dark matter needed to describe galaxies today matches exactly the amount of dark matter needed for the correct anisotropies at the time of recombination, roughly 13 billion years earlier. From the height of the first peak, you can see how strongly the ratio of visible to dark matter is constrained by the CMB data. In summary, we have a cosmological model that accurately describes the observed temperature fluctuations in the cosmic microwave background. This model is called Lambda-CDM, and its parameters are measured to high precision. Lambda labels the dark energy component, which contributes almost 70% of the energy density today, while CDM stands for cold dark matter that makes up most of the remaining 30%. Only a little less than 5% of the content of today's universe is stuff that we can actually see when we look out at the sky. As I've told you already, the amount of dark matter is independently confirmed by observing orbits of stars inside galaxies, which require additional invisible matter to account for their speed. Similarly, dark energy is confirmed independently by observing type 1a supernovae, which are used to measure the currently accelerated expansion of our universe. However, it was the observation of the fluctuations in the cosmic microwave background that tied up all loose ends and revolutionized our understanding of the history of our universe. The precise measurement of the matter-energy content is just the tip of the iceberg. The anisotropies of the microwave background are a goldmine for digging all the other cosmological parameters. They even test theories about how these fluctuations came into existence in an otherwise uniform universe. There is a popular theory that soon after the Big Bang, the universe underwent a rapid expansion called inflation. This expansion was so quick that even quantum fluctuations didn't have time to fluctuate. They were frozen into place, becoming classical perturbations in the young universe. Only when these fluctuations re-entered the horizon they began to evolve. They either oscillated like in the proton, electron, photon plasma, or collapsed under gravity, forming all the structures we see today. Can we ever make observations of the universe before the time of recombination and look deeper to the origin of the universe? The answer is yes and no again. With light it seems impossible to look behind the surface of the last scattering. However, there are two other forms of background radiation that can take us even closer to the Big Bang, at least in principle. One example is the neutrino background radiation. Neutrinos, which interact only very weakly with ordinary matter, decoupled from the rest of the universe around 1 second after the Big Bang, when the universe was about 10 billion degrees hot. Detecting these neutrinos is extremely challenging, and the fluctuations at this stage would have been much smaller, making them even harder to observe. And finally, another candidate is the primordial background of gravitational waves. They decoupled more or less immediately after the Big Bang. Currently, we observe gravitational waves from dramatic events like black hole or neutron star mergers, the brightest sources in our neighborhood, so to speak. We will need to overcome a few experimental challenges until we will be ready to measure the faint afterglow from the Big Bang directly. So while 380,000 years is the closest we have gotten so far with the CMB, neutrinos and gravitational waves might offer glimpses even closer to the Big Bang, though they remain a bit elusive for now. That's all for today. As always, leave your thoughts and recommendations in the comments, and I hope to see you again next time. Bye bye.